Okay, hi everybody.
Cool, loud and clear. That's awesome. Here's, so link to the talks. If you want to look up the talks, many of you, I imagine, are going to have watched them. I've put a link into the chat. All right, and it's 2:30, which means we should probably get started. Ready, Lori?
Ready.
All right. Oh yeah, this is like if you watch the numbers, people are just coming in. So it's 200, 200, 210. I'll wait a second until that sort of levels off a little bit. Welcome everybody. It's good to see so many of you here.
Yeah, this is exciting. At our very first ever high performance Python session at SciPy.
That's right. In virtual form too.
Yeah.
All right, we've got nearly 300 people. Click to get this t-shirt. That's a good question.
Is from last year. We build a time machine, I guess.
All right, let's wait until we hit 300 and then let's get started. How about that?
What are we at now? I can't see that.
280. Oh, you can't. 280. We're at 286 right now.
Okay.
Call audience to session in this talk. Oh, okay. Let's see. Is that under options? In the schedule part, I see. Okay. Call audience to session. So I'll do that. Ding dong. And there we go. 6:18. All right. That's what it took. Okay.
Okay.
Then I say let's get started. Well, okay. Welcome everyone to the first virtual high performance Python track at SciPy 2020, taking place in, I guess, cyberspace instead of Austin, which is a little sad. My name is Andreas Klockner. I work at the University of Illinois. Co-hosting the session together with Lori. I guess she might be over to my right.
Oh, hi everyone. I'm Lori Steffi. I work at NERSC, which is a Department of Energy Supercomputing Center in Berkeley, California. And I help take care of and support our many Python users there. So I'm really excited about this track.
And so I will be working in the background, pushing the buttons, while Lori is going to lead us through the session. So if you have any technical complaints, just try and message me. Otherwise, we're looking forward to having a great session with you all.
If you're wondering, I lost the coin toss, so I have to be. All right, so we have a short 1 hour and 15 minutes with you all. I'm really happy to have so many great experts and speakers in this session, so let's get right to it. So our first speaker and slide will be Christian Herold. So Andreas will get Christian's slide up on the screen, and we'll get Christian up, and then he'll have about 1 minute to kind of summarize what was in his video. If you haven't watched the videos, they're live on the NThought playlist, so check them out if you haven't. Okay. Oh yeah, here we go. All right.
Okay. Hello everybody. I'm Christian, and I'm working in the field of high performance computing. Furthermore, I'm working in the performance analysis of parallel applications. I lost the slide. Okay. And traditional HPC applications are low-level applications. They're using multiple low-level APIs for parallelization, for I/O, or for some example, algebra. So traditional HPC performance measurement tools are really good in measuring and analyzing performance of these low-level applications. Nowadays, we're getting more and more high-level applications from Python on our clusters. And now we realized that our support for such high-level applications is not so good. And that's in this talk, our contribution. We extended especially our tool ScoreP in order to measure the performance of Python applications. So we instrumented an automatic code instrumentation for Python application. We provided an API for creating own measurement points and for controlling the measurement of ScoreP from the Python level of the application. So that's it.
Okay, great. Well, thank you, Christian. So we've had one question, well, two questions come in so far. The one with the most upvotes is, can you profile number code, especially nested number calls?
If this is an native Python application, this should be not a problem. It depends a little bit what number is doing. I have actually not so much experience, but I don't think they calling sub-processes or spawning processes. That would be it could be a reason when it could fail, but yeah.
Okay. Do you have any Jupyter support?
Yuke, yeah. I mean, this is a case which we has actually not focused on. I think we should try it. Actually, we have never tried that. Because I have to also say here, the profiling is one of the part. We could also create really detailed traces, and that's for long-running applications. For example, like a Jupyter notebook, which runs maybe days. Not the use case. Yeah.
Okay. So some questions that Andreas and I had. Do you need to instrument your code to use this? Will it run out of the box?
From the Python side, we are just using this set profile and this set trace. For that, it's an on-the-fly instrumentation. I mean, it's where the interpreter executes the Python code. So there is no additional step for the user for instrumenting the code. Yeah.
Okay. Can you handle Dask, like Dask distributed, multiple node profiling?
Dask, we are working on that. It's not in that shape it is actually working, but we know and we're working. What is actually multi-node working is MPI for Pi. That's for multi-node working.
Okay, but can you profile with ScoreP any of these multi-node?
Yeah.
Okay.
Yeah. So from the ScoreP side, there's still the support for MPI, SHMEM, and such paradigms. Yeah.
Okay. Another question we have is, how much do I have to know about ScoreP to be effective? Can you talk about the learning curve?
Yeah. For such profiles which I presented, the learning curve is not so high, so you get very easy success. But when you have a really big application, which do a lot of things and which also maybe use a lot of different paradigms, for example, QDAR or MPI and such stuff, you need more knowledge to configure ScoreP, and this is a little bit besides this our contribution, yeah. But for that we providing every year tutorials and sessions for training how to use ScoreP and how to configure that. because at some point you have to fight against your measurement overhead, and that's sometimes not so easy.
Well, thank you, Christian. I'm sorry we don't have more time, but we have 10 speakers.
Okay, thank you.
So thank you. And I see a lot of questions that are kind of more general Python and HPC questions. So I'm kind of hoping maybe if we don't answer them now, we can kind of talk about it at the end. So I'm not ignoring you. I'm just trying to pick out something specific. Okay, well, thanks, Christian.
I just wanted to briefly interject on logistics, since we have a lot of talks and it's sometimes not entirely clear which question goes with which talk. The slides should all have a marker in the top right or top left about a single word that you can use at the beginning of the question to identify what talk you're asking about. It's not so much a concern for the first, but I think going forward we can make it less confusing for everyone if we do that.
Andreas, too, I think you can clear the questions between speakers if you want.
Oh, I can, okay. I would have to figure, I'll look into that.
Okay, it's fine.
Okay.
All right, well, our next speaker is going to be Ben Albrecht, who's from Cree. He's going to be talking about Arcuda. So I guess we'll get set up for Ben. Thank you, Christian.
Welcome.
So for those of you skeptics who are asking, why do I need fast Python, or how fast can Python be? I mean, I hope this session kind of speaks for itself, but they like Python, they're friendly, it's a friendly language, and they want to be able to scale without the additional headache of writing in C++. So here we are. All right, here's Ben.
Hello. Yes, so I'm Ben Albrecht. I'm at Cree. I spoke about Arcuda, a project that aims to enable terascale data science at interactive rates. And this was led by Mike Merrill with Bill Roos at the Department of Defense and supported by the Chapel team led by Brad Chamberlain. So Arcuda is a distributed data science library with a NumPy-like interface, and it aims to perform terascale data science operations within the human thought loop, enabling interactive sessions with data sets of these sizes. And the table on the right here is just a demonstration of this, where we have some data collected on 50 billion element arrays on 96 nodes of a Cray XC40. And you can see a number of common data science operations are able to finish either under a second or within the order of seconds on these terascale data sets. And I'm happy to take any questions.
All right, so here are the first few we have. Does Arcuda interoperate with Grid Engine or Slurm?
So the user is required to launch the actual Arcuda server onto Slurm or your workload manager. There is some built-in support for that to automate that, but that's as far as the integration goes.
Okay, this one, we have two people who would like to know, how did you choose the name Arcuda?
So I didn't choose the name. This was chosen by Mike Merrill and his team. I believe it's bear in Greek. He could probably say more. I think he's with us here today, and he could probably say more in the comments, the reasoning behind that.
Okay, are you supporting GPUs with Chapel or Arcuda?
Yeah, so GPU support is on our radar. We don't have GPU support today, but so Arcuda inheriting the functionality from Chapel. Chapel does not yet have GPU support, and that's a target in the next few releases as we transition to an LLVM backend. So once we're there, Arcuda will inherit GPU support as well. Okay, great.
Have you compared to dist arrays? There's several questions here. Do you have overlapping region support, and can you elastically scale up or down your number of workers?
Okay, so dist array, I don't think we've done comparisons to dist array, but I mentioned in my talk we're interested in benchmarking against the number of. There's a lot of technologies that have slight overlap in this space, so we're interested in getting apples to apples comparisons there. So that would be interesting going forward. For overlapping regions, so Chapel supports overlapping regions today. I'm not sure if this has been exposed in the distribution interface to Arcuda today, but that's certainly possible. And what was the last question?
Can you elastically scale up or down your number of workers?
So you have a fixed number of, so per operation, you can have a dynamic number of tasks running, which would correspond to your workers. So yes, but more general, I guess this isn't the question being asked, but being able to scale the number of nodes being run on a system is not something supported today.
Okay. And maybe last question. So can Arcuda be deployed on the cloud? How does it work with dynamic or auto scaling clusters? I guess that's sort of the question, but yeah, cloud capability.
Yeah, so Chapel is extremely portable and can run on the cloud, and therefore Arcuda can as well. And we've actually collected some timings on AWS EC2 instances. In terms of the dynamic scaling, again, I don't think we don't have support today for dynamic scaling of nodes, so we wouldn't have that support today.
Okay. All right. Well, thank you all for your questions. Thank you, Ben.
Thank you.
Our next speaker is going to be speaking about awkward array. And this is Jim Pivarsky. So we'll get Jim up. All right. Here's Jim. Go ahead, Jim.
All right. So is my slides up? It is. So my talk is about awkward arrays, which is what I call arrays that aren't rectangular like a tensor. So this includes any JSON-like structure, such as variable length nested lists and record-like objects with named fields. The example on the top of the screen here is a toy example, but datasets with this complexity are common in some scientific fields, like particle physics. The problem that we have is not just representing data like this, it's that we want to do calculations that depend on the structure, such as the ones below. There's a NumPy-like expression on the right and its pure Python equivalent on the left. Expressions can be more succinct with NumPy-like multidimensional slices, universal functions, broadcasting, and all that. And faster too, typically by an order of magnitude. So in my talk, I show how to use these awkward arrays in the sample analysis, including Numba, how it relates to Apache Arrow and Pandas, and go into more detail in the paper. So yeah, questions?
Okay, thanks, Jim. All right, so first question is, how does awkward's performance compare to JQ?
JQ?
I'm not familiar with JQ.
Yeah. Nope, I'm not either, so I can't say.
Okay, sorry, Ed. All right, will awkward extend or merge with the Xarray interface?
Well, it's different from Xarray because Xarray is still representing rectangular data structures.
I see. Okay, does awkward directly interface with other libraries like Pandas or SciPy?
Yeah. So, for instance, an awkward array can be a Pandas column. So you can make a data frame where some of the columns are awkward arrays. And what was the other one? SciPy. Any ufunc can automatically go through this. So this example here with NP square, that could be any ufunc.
Okay.
I actually tried some SciPy ufuncs.
Oh, that's great. All right. Do you plan to extend awkward into storing or loading? So can you add any I/O?
Yes. There's already Apache Arrow I/O, and we hope to use that as a stepping stone to Parquet. In earlier versions of this, we could convert to HDF5 files, but HDF5 is a flat array, so then you always needed this interpretation layer. So we prefer finding these formats that are already hierarchical.
I see. Okay, can awkward handle slicing columns when the records have keys of integers?
Oh, when the records have keys of integers, no. Interestingly enough, the records here are they're like structs. So the field names are part of its type. You can also have unnamed fields, so you can have tuples. So.
Okay, can you talk about your experience of getting Awkward to interface with Numba, and how did you work with the Numba developers?
Eventually. Actually, the work on a project like this involved Numba from a very early stage. Where at first I was just using Numba to, generate some Python code and use Numba to JIT it. But as we went through various iterations of this over a few years, eventually learned enough Numba internals to more effectively use their extending interface, and so it's basically Numba native now.
Okay, can you maybe contrast Awkward with sparse arrays?
Right. So sparse arrays are defined only at certain index positions, and you could express something. They are different. Let's see. So for a sparse array, what you want to do is you want to take some small dense array and logically map its indices onto some much larger space. And what Awkward array does is it describes deeply nested structures in some dense array. So it would be interesting actually to put the two of them together and have a sparse array map a large logical index space to a small dense space, which happen to be Awkward objects.
Okay, all right, maybe the last question. Can you talk about what you learned going from Awkward version 0 to version 1, what your biggest takeaways were?
So the Awkward 0 was written entirely in Python, and we did all of these columnar operations in NumPy, actually, using lots of tricks, some of them very clever. While that's great, it's amazing that you can do that. It's amazing that that NumPy is versatile enough to describe stuff like this and do these kinds of operations. For maintainability, just writing it more simply, without tricks in C++, and then putting a Python layer on top of that, saves you from the 1,000 cuts of here at some point I'm trying to find the maximum of an array, but it's empty. Stuff like that. So that's what but we wouldn't have gone through the enormous effort of writing this C++ package if we didn't already know it was popular. So having the Awkward 0 was quickly written in Python, got a user base, got feedback, found out where interface mistakes were, was very useful to go that stepping stone.
Okay, great. Well, thank you, Jim. And I guess we'll switch over now to Boost Histogram, which is we're going to have Henry Schreiner coming up. So go ahead and give us your Boost questions for Henry. Well,
he's coming.
Okay. All right. Another meta question that came up in chat was, how does Python compare to C or C++? And I think the answer is if you're using optimized libraries like NumPy or SciPy or Numba, Python's not as slow as its reputation might sound for you skeptics out there. So if you're writing pure Python, maybe not. All right. Anyway, go ahead, Henry.
Okay, so I'm Henry Schreiner. My talk was overviewing histograms as objects, and it was discussing the Boost Histogram library. So histogram is really a composable collection of a storage and one or more axes. And these come in many forms. A axis describes a conversion between a data coordinate and a bin coordinate. And you can even do categorical axes with instance strings. Axes can grow. You can have bins for out-of-range values, or you can even have circular axes. And then you have the same API for 1D or 32D. So this, with something like this, you can fill multiple times. You can manipulate these after you fill, and all the axis information just gets transmitted along with the manipulations. You can slice in either coordinates system. You can project, rebin, and then it's Pythonic, and there's lots of binaries available. You can bundle even collections of histograms as axes, and that really transforms the way you think about analyses, much the same way that group by changes the way you think about pandas. And it's fast. So 2D regular binning is, and that's just an image, is over 10 times faster than NumPy on a single core, and even faster if you use threads. And this is using it as a drop-in replacement for NumPy, which you can do, but it's better to use histograms as objects.
Okay, thanks for the overview. So the first question is, will boost hist be the default implementation for hist in SciPy?
For hist in SciPy or in scikit-hep? Currently we have hist as is a sort of a user-facing package that sits on top of this. You can think of boost histogram sort of as NumPy, and then hist is sort of a user-facing version that does do things like plotting, and boost histogram is the implementation behind that. Okay.
Can you talk about what the major motivating use case was? Where did this effort come from?
So this is part of the scikit-hep project, is trying to build a set of tools for high energy physics usage. Awkward, boost histogram, and several other tools are built sort of to support high energy physics in Python. High energy physics traditionally has been C++ in the legacy root framework.
Well, welcome high energy physicists in Python. Okay, next question. Matplotlib histogram takes a lot of time for calculating histograms for large images, especially satellite images. Does boost hist provide relief in terms of computation speed?
Yes, it should. I'd have to try it on an image that size, but you can do the calculation itself in boost histogram, and then you just simply plot. You could do, if you're worried about such a large image, I would probably use MShow versus mesh grid. But then that actual plotting of the image would be fast, and you could do it in any library, including Matplotlib. But the actual calculation should be at least 10 times faster, because it's using that same non-regular, that same regular binning 2D that's slow in NumPy, which falls back to the same thing as a non-regular binning.
I see. Next question. Where do you see the boundary between the histogram as a data storage object versus the histogram as a graphical representation of the data? Do you hope for BH or hist to handle tick marks, color palettes, trellises? Or do you see that as something additional libraries would handle?
Those sorts of things would be something the graphical library would handle. So boost histogram would do no plotting. It just does the filling and then manipulation. And then hist will provide adapters to currently just Matplotlib. But that basically just sets up the image for you, and then you would call the standard Matplotlib things to change tick marks or whatever you want to change color palettes, and you can do that.
Okay. So when you say fast, do you have any notion of how close to the peak you are?
I think we're doing quite well. I think probably usually within about a factor of 2 or so. If you look at my blog, there's actually a list of different methods doing everything from PyBind 11 to Numba and various other ways of doing this. And I think we are within maybe a factor of 2 or 3. And because this is an object, you can later add specific specializations to, say, if you want to actually have a specialization for regular 2D bending, you could do that, and you might be able to get an extra, maybe up to a factor of 2. But that's about all I think we have.
Impressive. Okay, I guess last question. how does this interface with the rest of the ecosystem? Can you use this object directly, like in NumPy, for example?
We try to interface as well as we can. The one thing we can't do is we can't teach, for example, matplotlib to understand a boost histogram, though that might be something to do in the future. At some point, we're trying to set up a standard API so that you would have a way to communicate histograms using a protocol, saying that a histogram object should have these things. But it just naturally works inside NumPy. It provides a buffer API. It provides the pickles, set state, get state. It provides these smart views, which are just indie array subclasses that let you work with the data inside the histogram in a way that's natural inside NumPy.
Okay. Well, thank you very much, Henry. Next up, we'll have John Mees. He's going to be talking about GPU support for data shader via Rapids. If anyone has any meta questions, we can talk about that while Andreas gets drawn up.
I think I'm here.
All right, welcome.
Thank you. All right, so this talk was about data shader. So data shader, as general background, is a high-performance Python library designed to basically support building visual representations of large data sets. So it does a lot of work with sort of large scatter plots, large line plots, does some work on meshes and graph layout algorithms and things like that. It's implemented in pure Python with a lot of heavy use on NumPy and Dask. So a lot of data shader's algorithms are very well suited for highly parallel GPU style acceleration. It's something that the project has been interested in doing for a long time, adding GPU support. But it's always been pretty impractical for two main reasons. And this talk, I kind of go through those reasons and then talk about how Rapids is something that we've used to help mitigate that. So the first reason is that data transfer from CPU to GPU memory is relatively slow for the large kind of data sets that data shader is working with. And on a more sort of pragmatic side, it hasn't been practical to have sort of separate code paths for CPU and GPU implementations of things. So data shader being pure Python, we didn't want to have a whole separate like C or C++ code path for doing the GPU version. That would have been maintenance nightmare for a bunch of reasons, and would have had us get a lot of things out of sync. So in the last couple of years, as Rapids has been growing in maturity, we've been able to incorporate several Rapids technologies into data shader to support GPU acceleration, and have achieved a lot of code reuse across the CPU and GPU code paths, and a good speed up on various use cases. And this talk, if you're interested and haven't seen it yet, is sort of a discussion of how we were able to achieve that, and hopefully it would be useful for other folks that are interested in evaluating adding GPU support to sort of existing libraries.
Okay, thanks, John. So I have a question about the demo that you showed at the end of your video. I'm just wondering, like, what kind of system were you running on? How many GPUs does it take to produce that kind of rendering?
That demo was run on a GPU with, I believe, 24 gigabytes of RAM. It was one of the GTX series. So a single server, a single GPU, but it's a large GPU.
Okay. Would what you showed be at all possible on a multi-CPU system? Is there any kind of multi-node backend in data shader? Yeah, so data shader already had Dask support. So we can already scale out to pretty large data sets using Dask across multiple nodes, multiple servers. So this is really more about responsiveness and getting faster response times, like when you're panning and zooming and refreshing, regenerating the plots. The GPU support had a big advantage for responsiveness for kind of, I guess, on the order of data sets that ended up being on the order of like 5 to 10 gigabytes in memory. Going larger than that, you'd either need to go to multiple nodes, and Datashare does support multiple GPU nodes the same way, but you get best responsiveness for a single GPU for that size data set. Does data shader work with .nc file format? .nc? Yeah, I'm not familiar with that. But that's, I'm not familiar with that, unfortunately. Well, sorry, Rich.
In terms of data structures, it works with pandas data frames, DAS data frames, and now QDF data frames and X-array data arrays. So it's more a matter of whether that format could be loaded into one of those data structures.
Okay. Does the dataset need to fit on the GPU? Do you need to have any additional code, I guess, to fit the data? I think that's what they mean.
Yeah. So for this approach, it's using like QDF as the data frame library, and so with QDF, you do have to have enough GPU memory to hold the entire data frame. It doesn't do like any spilling over into CPU memory. So that is a kind of have to be this sort of sweet spot where you have enough data to make it worthwhile, but also not more than your GPU can handle.
Okay. All right. Clarification. So the data format the user our person was asking about was netcdf files.
Okay. Yeah. So netcdf, you can load those into X-array and then get those into pandas data frames pretty smoothly. So that would be the path.
Okay. Can you talk about the data movement time? Will preloading data into the GPU avoid copying and maybe speed up the application?
Right. So the way to avoid copying is basically using the sort of rapid ecosystem. So, for example, when you're working with QDF data frames, the data is already pushed over to the GPU into GPU memory. So data share itself doesn't have to do the transfer. So data share doesn't do the transfer itself. It just works with the GPU data structures like the QDF data frame, and then it can produce GPU data structures on the other side. So the user gets to decide sort of when in the pipeline they need to do the transfer, and data share can just work on data after it's already transferred. So that's how that problem is practically worked around.
Okay. Next question. This person says, thanks for the great talk. On the data shader slide overview, you showed going from data to a plot. Can data shader create a table from a given image as well, or are you planning on that?
I'm not sure I fully understand. So the output data shader is an image. It can be it can be either a scalar heat map style image, or it can be an RGB 3-color image. But all of the data types and visualization types are transformed into that image. And then to display them interactively, you need to combine data shader with something like bokeh or plotly to do the sort of display of axes and handle the panning and zooming and that kind of stuff.
Okay, thanks. And then maybe the last question. So it looks like some of your examples were histograms. Can you talk about pros and cons versus boost histogram?
Yeah, there is some overlap. I haven't used a histogram, so I think there is some interesting overlap there. The data share has these core algorithms for doing two-dimensional binning. It doesn't do general n-dimensional histogramming. It's basically just two-dimensional at this point. It's all implemented in Numba, so it's a sort of different implementation. And one of data shader's, I think, sort of secondary goals is to be sort of a platform or experiment for how far you can push pure Python in terms of performance. So it'd be interesting to compare. It'd be interesting to see performance comparisons between them, but I don't have a guess as to how that would turn out at this point.
Okay. All right. Well, thank you very much, John. And next we'll have Adam Thompson talking about Cree Signal and how they've used Numba and SciPy. So thank you, Andreas.
He's on the way.
Okay.
Hey, everybody.
All right.
Excellent. So it's kind of funny. I think I'm sort of surprised I'm the first with a quad chart. So I'm showing my government roots, right? Anyway, Cree Signal is a GPU accelerated library targeting signal processing, core functions, and borrows from the SciPy Signal API. So the idea here is to provide GPU type speeds using the same API that we all know and love. This is also a Rapids. You've heard that a couple times. This is NVIDIA's open source GPU accelerated data science package. And the interesting thing here is this is the only library that doesn't have a native C++ or CUDA actual software layer. So all of the software development is from Python. We're getting typically 1 to 2 orders of magnitude speed improvement over SciPy Signal on CPU. with minimal changes to the API. So you can see there on the bottom left corner. And then the other thing that we stumbled in here is this is a really compelling recipe for building GPU accelerated Python applications, for things that are outside of the signal processing domain by leveraging the ecosystem. And then if there isn't coverage, going to Numba, CUDA kernels, and then raw CuPy CUDA kernels.
Okay, well, thanks, Adam. So your first question is actually like 3 questions, but does Cree Signal integrate with JAX or provide gradients?
That is a great question. It doesn't currently integrate with JAX, and it is also not differentiable. So, one of the differences in some of the questions that we get are, could you have built this with something like PyTorch native? And one of the reasons I didn't go down that route was because of the complex value numerical support. So end-to-end Cree Signal would not be differentiable. But what you could do is you could do your pre-processing, get to a domain, zero copy transfer over to something like PyTorch via the CUDA array interface, and then do backprop on that. But this is something that we're certainly looking into.
Okay, and the second part of that question is, can it scale on multi-nodes, maybe via Dask or Legate?
We haven't explicitly tested that out. So this is solely single GPU currently. It's been targeted primarily towards the software-defined radio community originally. So one of the interesting things that people are doing is they're plugging in like an RTL SDR, which is a little $30 software-defined radio, and they can do like demodulation of the entire FM spectrum, in within Cree Signal. So again, looking towards multi-node, multi-GPU is on the roadmap as well.
Okay, can you currently handle streaming data?
We can. So it's not what we do, and this is interesting, particularly for signal processing pipelines, is you have to transfer small buffers of data because you don't want to drop radio packets. So one of the things that we do is we have set up a zero copy buffer between CPU and GPU. This is using just a CUDA mapped array. So this is handling. It's essentially enabling a DMA between CPU and GPU for this. So it's a roundabout way for handling streaming data. So it is suited for online signal processing as well.
Okay, can you talk about where most of your speed up came from when you moved from CPU to GPU? Do you know where the bottlenecks were?
So a lot of the bottlenecks were just in sort of the matrix multiplies. So if you look, and look through some of the slides that we've done, the biggest speed ups are things like large scale FFTs, large scale, like the polyphase resampler is, creating a whole bunch of filter banks and going through multiplications on there. So a lot of it is just using, GPUs for what GPUs are super good at, right? So just dense linear algebra. Okay.
Do you know at all? Have you done a roofline analysis? Do you know how fast your kernels are?
So we haven't written raw CUDA code for the functions within Cree Signal that have been ported to this custom CuPy CUDA. But the thing is that as we crawl, walk, run from these drop-in library replacements to custom Numba CUDA kernels to raw CuPy CUDA kernels, you essentially just have this just-in-time compilation overhead. So if you pre-compile that and cache it, it should reach native CUDA speeds. But we haven't, formally written a .cu CUDA file and done a bake-off there.
Okay. Have you thought about making complex values differentiable in the future? The question cites a GitHub that you can look at. I won't read you the link, but
I would love to. So one of the things that I want is complex value support in something like cuDNN. Right now, if you're doing complex multiplication, you have to essentially do your FOIL method that you learned in algebra, and that's slow, right? So that's 4 times the speed because you're using 4 times the compute to there. So it's something that we're looking into. It's something that I'm intimately involved with, and also want to see because these complex valued neural networks are taking phase information into account And that's important not only for communications and wireless signals, but also imagery.
Okay, I guess last question. So what are the next steps for Cree Signal?
So Cree Signal, this is my call to action with the community. And I realized I didn't introduce myself. I didn't do any of that stuff. I was just like, oh my God, I'm on the screen. But anyway, we're at a place where we'd really like to see what is interesting the signal processing community. So we're looking for more performance. We're going through the library to say, what did we just do a drop-in replacement where we can get easy additional performance? But signal processing is huge. So whether you're interested in speech or audio or RF data, just interact with us on our GitHub repository and be happy to move forward together.
Okay. All right. Well, thank you very much, Adam. And we'll get ready for our next presenter, Antoine Dwarjin. I hope I said that right. He's going to talk about fluctuating X-ray scattering in real time.
Hi.
Go ahead.
Oh, yeah. Hi. So my name is Antoine Dujardin. I work at SLAC National Accelerator Laboratory, which is one of the 17 US Department of Energy national labs. One element of SLAC is the LINAC coherent light source, which is essentially a 2 miles long accelerator that produces a very powerful X-ray free electron laser. And currently we produce 120 images per second, but we are currently upgrading the system to bring it up to 1 million images per second. Now, that brings a lot of new challenges, and it's not possible to deal with the old algorithm we had that were somewhat inefficient. No, we really need to get everything we can from the compute power we use, and some application might require up to exascale processing. So in this talk, we are going to focus on one specific case study, fluctuation X-ray scattering. And we have a set of 2D images, one 2D image for each capture, and we expanded them in a 3D space and then average everything. It's extremely compute intensive and represented the vast majority of our application. And so we show that we can actually accelerate that by a tremendous amount just by staying within the tools offered by Python, NumPy, and Numba. So applying some batching, optimizing the math rather than the computation, and then paying attention to the contiguity of the memory alignment of the data, and we obtain a 40x speed up. That was for one process. Then we look at the parallelization, and we use a tool called Pygen, which is an interface to the Legion programming system. It allows us to separate the logic of the code from its parallel execution. And so Legion is a system-wide, task-based, and data-centric system that I introduced a little bit in the talk.
Okay, so the first question is why Pygen and not Legion directly?
We code in Python, and we want Legion allow you to define tasks to be executed rather than function, and it's easier to just decorate them with decorators, some annotation that are integrated to Python. So Python is just the name of the Legion bindings, so it's integrated to Legion. It's done by the Legion developers. Okay.
Can you talk about the resolution of the image data that you're dealing with?
So here for the toy example, we consider that the images are already binned on polar coordinates with 300 pixels on the radial dimension and 256 angular bins.
Okay, so I saw that plot where you're part of the way there, but you're not as fast as you need to be to process all the data coming from LCLS2. So can you talk about what your current bottleneck is and how you think you'll try to improve that?
Well, in the beginning, the real bottleneck was the computation. Now, after accelerating this and parallelizing it, we are at 15,000 images per second. And that's what we expect LCLS to be in 5 years. So the 1 million images per second might not be in the FXS application. For FXS, we could be at 100,000, and that would be for 2026. So we are not really concerned about our ability to follow up with the data at this rate. We think that the application is good enough on the compute power side for now. And so now we need to plug all the pieces, because this is just an app that's supposed to run on the supercomputer. Now we need to make sure that the data that's produced as LCLS can be shipped correctly, can be analyzed directly, and that the result can then be sent back to the user.
Okay. Since you're already using Legion, have you thought about Legate? That'll be our last talk of the session, but do you think that would be another option? We thought about it, but I think that we rely a bit more on the tasks, and Legate is great to work with NumPy arrays. In the new application on which we are working, we are using other libraries than NumPy, and so we don't expect them to play nicely with Legate. And when this application has been coded, Legate was not available yet. If we had to do this specific application again, then I guess we would consider Legate. Yes. Okay, but you're too far along to scrap it and start again.
Yeah.
Yeah. Okay, have you done any roofline analysis? Do you know how close to peak or how good your kernels are?
Sorry, can you say that again?
Have you done any analysis on your kernels? Do you know where they fall in the roofline or how close to peak they are?
Well, at the end, we ended up with a NumPy dot product that we pay attention to the alignment, and we really rely on NumPy to do the right thing, the best thing. We didn't try to see if we could optimize that, because we felt like we were on close to the bottom to what Python was able to give us through NumPy, and that was good enough. So could we have done better? That's possible. We didn't really try to count.
Okay. All right. And then this will be the last question. So is the challenge the image analysis, the speed of image capture, or both? And that's the first part.
The big challenge is that we will be processing 1 million images per second. And at that rate, you can't even save everything. You can't even extract everything from the detector. So first you need to have some data system on the detector, then you need to send it directly to the supercomputer. And we don't have a supercomputer, at least not one of the exascale at Slack. So we need to be able to send everything to NERSC, process everything. And so we do have a lot of bottlenecks on the way. And the app used to be one of the main bottlenecks. And so now it's no longer, but we have a lot of them.
Okay, all right. Yeah. Last part of the same question is every scientist doing the same kind of analysis, or do different groups need different kinds of processing?
Different groups do different kind of processing, and that worked well when we had manageable amount of data where we could save everything and then let the scientists use their own data. Now that we are producing so much more, we can't expect scientists to be able to deal with that tremendous amount of data, which is a normal tool. So we are trying to build new algorithms and new abstractions to make that easier. And there is a part of just making it easier, and there is a part of making more tools available. And so this is more of a case study also on our part to see how we can help scientists develop applications. Okay. Well, thank you very much, Antoine. We'll move on to our next speaker, Roland Thomas, who's going to be talking about running Jupyter at NERSC. I was just realizing we don't have a high-performance Python channel on the Slack, so maybe I'll add one and we can continue discussing afterwards. Anyway, go ahead, Roland.
Am I there? Do you hear me?
Yes.
All right, thank you so much. I'm Roland Thomas. I'm a data architect at NERSC, which is the Supercomputing Center at Lawrence Berkeley Laboratory in Berkeley, California. The background of this talk is really the phenomenal growth of Python for scientific computing. We just saw a really interesting discussion about work being done at Slack and the experimental work that's being done there, and shipping the data off to a supercomputer at a place like NERSC to turn the data into insight and get it back to the people who are actually at the facility. And so a lot of users that have come to NERSC in the past 5 years are experimental or observational data scientists, and they do a lot of their programming in Python because of a variety of reasons. I think everybody at SciPy knows what the benefits and drawbacks are of using Python for scientific computing. Basically, when Python users show up at a place like NERSC, they expect to be able to have the whole ecosystem there, and Jupyter is a part of that ecosystem. Of course, Jupyter is a way for people to run kernels in a number of different languages, but the primary use case for Jupyter at NERSC is through Python. It's becoming an essential interface to high performance computing resources. We have about 700 users logging in per month to Jupyter compared to all of our other login nodes where users come in via SSH. That's about a quarter of that. So it's a pretty substantial number of users who are trying to use Jupyter to interact with compute, massive storage, or high performance networking. For users, it provides a rich user interface experience compared to SSH-based logins. There are obviously the benefits of using notebooks on top of high performance resources. And for us in HPC centers, Jupyter is a new way to streamline delivery of services and resources to our users. So in this talk, what I wanted to do was create an entertaining talk. I hope it was entertaining, explaining how we make our resources available to users, what our deployment strategy looks like, what a guided tour is, basically a guided tour of the service, and some of our lessons learned. So there are two audiences for this talk. One is users, so I hope there's an appreciation there maybe behind what we're doing in order to provide Jupyter to our users, but also people at other centers who are interested in providing Jupyter as a means of access to their resources.
Okay, so we've got several questions already. So do you allow users to install their own packages? And if yes, how do you make sure this doesn't break compatibility?
We do allow users to install their own packages. The Python strategy at NERSC for about the past 5 years has been to encourage adoption of Conda environments. Prior to that, NERSC was doing builds of Python and Python packages for users. And at that point, that wasn't really sustainable. What really changed the feasibility of Conda environments for our users was the introduction of MKL into NumPy and SciPy there. So after that, a lot of users really were very happy with their ability to construct environments on the fly and manage those themselves. We kind of gave the locus of control of the software over to the users. And I think that that's been a pretty popular approach. How do we ensure issues with compatibility? Really, those are things that pop up only when people are trying to interact with the high performance interconnect, say through MPI, in particular for MPI for Pi. We provide them with a recipe to do that build correctly. It's actually pretty straightforward. But most of the time, I'd say like the thing that becomes a problem is people with really extended Python paths bringing in stuff from all kinds of different environments, maybe from other people even. And so we help users debug those issues. So even though we deliver Python through Conda environments, we don't abandon the users and just say, hey, you're on your own.
Okay, can you talk about are Jupyters at NERSC served or run in containers, and can users submit containerized jobs?
So Jupyter at NERSC, Jupyter notebooks at NERSC are mostly, for the most part, launched outside of containers, basically on, I guess, what you'd call bare metal, to use a kind of old term. And they're launched on, for the most part, users are launching notebooks on nodes that have been set aside from the login node pool for Jupyter. Jupyter itself is being run bare metal off of a centralized installation that we provide there. Users can run kernels that are using a container technology called Shifter. So if they have a Docker container, they can push that to a registry and then pull it down to our supercomputer, and then they can create a custom kernel that uses that container. We're working on streamlining that process in two ways. One is a concept of a kind of binder for HPC, which kind of bundles up the creation of these environments and helps with the deployment. My colleagues in the computational research division at Berkeley Lab are working on that. And another one is trying to figure out a way that users can manage the entire Jupyter stack for themselves, and that would probably be done through containers. Because with a centralized installation, we kind of make the decision about what extensions are going to be installed, and we kind of would like to put that back in the hands of users. But the Jupyter Lab architecture kind of right now doesn't allow for that. But I think we have a path forward.
Okay, there's like 10 questions here, so I'm sorry we're not going to get to all of them, but you should take a look at them when you're off screen and maybe you
Are you giving me homework?
Yeah, people watched. Okay, so can you comment about how you make sure there are enough resources when people submit jobs for interactive versus batch?
So for notebooks that are launched on batch nodes, we have a set of nodes that are set aside specifically for Jupyter. Excuse me, and access to those to that partition is on a request by request basis. I think there are about 50 users right now who have the ability to do that. They get charged for this, so it isn't free like the shared node notebooks, but people are aware of that. And so we're okay right now with those 10 nodes where we're not yet, we haven't reached capacity. All those 45, 50 people are not on at the same time. So we don't really have a resource problem there. However, we anticipate that that's going to be an important way for people to run Jupyter at NERSC, especially with the new system coming in with GPUs on those nodes. And so we are working on ways to, and there are a number of solutions already in place at a few other HPC centers that are very interesting, like sliding reservations and kind of real-time kind of queues where you can slot in a job, maybe not at the highest priority that's available for real-time processing, but something that kind of gets you ahead of the queue. The challenge there, of course, is trying to discourage users from abusing that kind of privilege.
Okay, and last question, almost out of time. So can you talk about advice for helping other institutions get support for Jupyter powered, for basically Jupyter and HPC?
So there's a community of HPC centers that are working together to figure out the best practices and create kind of a shared a collection of shared best practices for deploying Jupyter on our hardware. And we had a workshop last year. There are a few mailing lists, but they're not terribly active. But I think, as with everything in the Jupyter community, the answer usually comes back to the discourse, the Jupyter discourse. There are HPC Center folks who are active there, and you just tag messages with HPC, and you can start a conversation with them. We are extremely happy to have conversations with people from other HPC centers and share our experience with them and learn from them, because I don't think we know everything. So reach out to us and we can start a conversation about what we're doing and find out what you're doing.
Okay, great. Well, thank you very much, Roland. All right, next up, we're going to have Ralph Koob. He's going to be talking about magnetic fusion energy and real-time analysis.
So I've been trying to find Ralph, and I've been trying to get him to say hi. We have one Ralph in the room. If Ralph could say hi, that would help me a lot. Otherwise, I'm going to try and blindly add this Ralph in the hope that it's him. Let's see, he's accepted and connecting.
All right, I hope it's the right Ralph.
Hi. Right.
Okay. Hi, Ralph, welcome. Go ahead.
Okay, cool. So we have a rather domain-specific problem in our talk. So we developed a solution to a problem we have in fusion energy, and that is the timescale on which we perform data analysis. fusion energy has rather big experiments. They cost between 1 million and 100 million, and a large people are involved in operating these big machines and performing the experiments. So an experiment, we have the machines we have, they're called tokamaks, and they are shown in the upper left. And underneath this purple plasma donut, you can actually see a person standing 2 meters, and that is to scale. So those are really big experiments. And the way they operate is they run a plasma pulse, and this pulse runs a couple of seconds up to a minute. And in this time, we want to gather as much data about the plasma as possible. So we are using a lot of diagnostics to probe the plasma. On the right, you see the panorama of the outer wall of the D3D tokamak, which is operated by General Atomics in San Diego. And there are quite a lot of, you see quite a lot of diagnostics that are installed. So in these 10 seconds to a minute, all these diagnostics gather a lot of data. Once the plasma pulse has ended, the machine needs to cool down because the tokamak contains cryogenic components. That takes about 10, 20, 30 minutes, and then the machine is ready for the next shot. And what we want to do is we want to put data analysis on the time scale between the shots, so that the people who are running the experiments can use information from these data analysis to make better decisions about the next shot. So what we did was develop a streaming framework where data can be streamed from an experimental facility to a supercomputer. And this framework then allows us to run data analysis on the supercomputer. So in my talk, I explain how we built that framework, and I illustrate the workflow where data is streamed from a fusion facility in South Korea to NERSC. The data is streamed with about 500 megabytes per second. We're talking about relatively small data sets, 1 to 5 gigabytes. And we accelerate the data analysis by a factor of 100 so that it runs on a medium-sized allocation. I think it was 4 or 16 nodes on Cori within 4 minutes. And with that, by giving the operators the results of the data analysis on that time scale, we hope that they can make better decisions about the next experiment. So we are using standard Python libraries, namely MPI for Pi to facilitate distributed computing. We are using queues for multiprocessing. We are using Cython to facilitate, which allows us to run the data analysis routines and multithreads. And we are using advanced I/O library. It's called RDOS2, which is developed by the Department of Energy and is used in many codes that run on supercomputers.
Okay, thanks, Ralph. So you mentioned the 100x speedup. So did you do any code optimization, or is that just because you have more resources for your calculation?
No, that is code optimization. So we are using legacy data analysis routines that are developed by colleagues in Korea. So they have their own set of routines, and we ported them to Cython so we can run them multi-threaded.
Okay.
And another thing that is helpful is that the analysis is chunked. So the data is streamed in. I think it's 5 seconds of imaging data. And it's broken down to data packages, so the analysis can be performed embarrassingly parallel.
Okay, can you talk about how you overcame the GIL with your multi-threaded implementation? What libraries are you using?
Basically Cython. So in Cython, you can use parallel for loop, I think, and you run it within the no GIL clause. So you have to do some work with Cython so that you don't call any Python libraries within that no GIL block. But once you have solved that, it's very nice parallelizable. And when you're developing in Cython, they also have a visual tool that shows you the lines of the code which still depend on the Python library. So that's very comfortable. That's very good help in developing these analysis routines.
Okay, it's good to hear about your experience with Python. Do you think GPUs would be a good fit for your workflow, and are you considering them?
We are considering them, and since we did the legwork of porting all the analysis code to Python, it should be relatively straightforward to developing a GPU implementation.
Okay. Can you talk about what your biggest obstacles are, or what your current bottlenecks are?
They are not really bottlenecks so much, but more capabilities of the framework. So we have shown that we can perform a standard analysis on the relevant time scale. That is, instead of a couple of hours, you can run it in a couple of minutes. And now the next steps are incorporating multiple data sources and also making the framework adaptive. So you may not want to just blindly stream the data, but you may want to focus only on the interesting data. So in this framework, we hope we can use some some machine learning tools to which would give us a classifier and only stream interesting data, where interesting would be defined by the machine learning classifier. We're looking into using autoencoders and variational autoencoders for data compression, and then also some higher level data analysis is on our to-do list, so that that you can combine data from multiple diagnostics.
Okay, last question. Are you planning to generalize or kind of release this in the hope that maybe other experiments could also benefit from your tools?
It's on GitHub, and I'm happy to discuss lessons learned in our approach when people approach us. I think the GitHub link is in our SciPy proceedings paper. So we are not really generalizing, because it's very hard to generalize, right? You have 10 to 100 different diagnostics. Each one produces their own data set. They have different sampling times. They have different resolutions, and it often requires some work to compare data from multiple diagnostics into one. So there's no obvious way of generalizing.
Okay. All right, well, thank you very much, Ralph. This brings us to our final talk of the session. Sorry, I know we're running a little behind, but we'll be hearing from Michael Bauer, who's here to talk about Leagate. And yeah, we made a high-performance Python Slack channel, so feel free to continue talking about HPC and Python for the rest of SciPy on our channel.
Mike's on the way.
All right. Thanks, Andreas. Thank you for all your work behind the scenes, Andreas.
Still says accepted and connecting. Okay, we're good.
All right. Welcome, Mike.
Okay. Wait for the slide to pop up here. Hey, great. Thanks. So I'm Mike Bauer. I'm a research scientist in NVIDIA Research. And so talk a little bit about Leagate NumPy. Leagate NumPy is designed to be a drop-in replacement for canonical NumPy, which means you really only need to change that one import statement. And really, we think we're the first system out there that really lets you sort of translate canonical NumPy programs to run on any number of GPUs. So that means, you should be able to take a NumPy program like the one in the middle here and run on everything from like a single GPU in your desktop to a cluster of to a bunch of GPUs in like a DGX box, out to like the Selene supercomputer, which is hundreds of GPUs, or even on a machine like the Summit supercomputer, which has thousands of GPUs. And so we really think that's crucial for data scientists. And so Leagate is really endeavoring to achieve that. So I want to sort of give a little brief advertisement for going to watch the talk. And I think, the contributions you should take away from Leagate are that, it provides scaling out to hundreds of GPUs. It does this by sitting on top of a high-performance runtime system called Legion, which, just to be clear, is the same Legion that was being talked about in the X-ray or in the X-ray session earlier. And Legion has been running on supercomputers all over the world for many, many years. It has native support for GPUs and fast interconnects. And we talk a lot about how we actually use those kinds of features to get really great performance out of Leagate NumPy and really be able to target it. And finally, the last thing I'll say is that Leagate NumPy has been all about NumPy so far. We're having work on other Python libraries now. I won't say which ones here, but Effectively, in the process of that, we're actually looking at building an interface that's sort of Arrow-like, but for distributed memory kinds of libraries. And so if there are folks out there who have interest in that, you should probably watch the talk. I'll get to that stuff at the end of my talk. But and also, if people have opinions on what distributed memory Arrow interface would look like, we're interested in talking with you and collaborating with you. So with that, I think I'll open up for questions.
Okay, thank you. All right, so first question is Legate available in Conda or pip, or is it still only in NVIDIA Dev?
No, it's still only available under an early access release on developer.nvidia.com. The reason for that is, a little bit above my pay grade. I'm not allowed to make decisions about what gets open sourced at NVIDIA and not. I would encourage anybody who wants to see it in Conda to email legate@nvidia.com and sort of express your use case and give sort of the managers who make those kind of decisions sort of some input into what you see what you see as your use case and how having it open sourced and being in Conda would be helpful to you.
Okay, great. So it's kind of a call to action from us, I guess. It
is, yes. I would very much like it to be open source, but I don't have control over that.
Okay. Can you contrast Legate with CuPy?
Sure. So I think CuPy has been a really great project and sort of demonstrated, the power of GPUs. And CuPy provides a drop-in replacement, for NumPy on one GPU. I think you'll see in our performance results, the performance results on one GPU between Legate and CuPy are pretty much the same. There's some small differences, but they're effectively the same. I think the difference for Legate is that it effectively allows you to take a NumPy program and scale it out to any number of GPUs. Sort of grow your arrays and have them span multiple GPUs both within your node as well as across multiple nodes, sort of transparently. CuPy has support for multiple GPUs, but it's not drop-in NumPy replacement support. Like effectively, you have to write at a lower level of abstraction to get that multi-GPU support. So Legate, sort of does that multi-GPU support for free, and then it also goes multi-node, which I don't think CuPy has any facilities for.
Okay. Have you thought at all about fault tolerance? What if a node goes down in the middle of a Legate computation?
Yeah, so there's actually been a long-running course of research inside of the Legion programming system for a while, and actually we have some fault tolerance support inside of Legion for handling cases where we lose nodes and stuff. I would say it's not actually incorporated into Legate NumPy yet. Sort of a little bit experimental part of Legion right now. Hasn't made it into our master branch yet. When it does, that'll sort of transparently become available for Legate NumPy. And I'm expecting that to happen in the next year or so. But timelines change and stuff, and so I don't want to stake myself to any promises. But once Legion has fault tolerance, then Legate will implicitly have that as well.
Okay. Can you talk about how it interfaces with libraries like NumPy? Is it directly compatible?
Yes, you can actually use NumPy and Legate directly in the same program. Effectively, you can import Legate NumPy as some name and import NumPy as NP. And what will happen is effectively NumPy will just work with inside of your processes on a node. So effectively, if you have a multi-node job with NumPy, what that means is you're probably going to be passing in the same copy of a NumPy array from every node. What Legate is really good at doing is it'll actually be able to use your buffer in place. So effectively, you won't have to copy data into a Legate array when you pass in a NumPy array directly into it. We'll effectively learn, we can use your data right where it is. So we're using the normal Python array interface to interoperate. And so you can interoperate Legate NumPy and normal NumPy in the same Python program without any problems.
Okay, thanks. And last question. So can you specify or benefit from efficient data types or special dimensions if you're passing them to Legate?
Yeah, so I think so far we're pretty much, Legate is still sort of an experimental research project, which is why it's under an early access release. And so right now we're mostly supporting just fundamental data types. So, all 16, 32, 64-bit ints and floats and unsigned ints and bools and those kinds of things. If you have structures for your NumPy types, we haven't directly supported those yet. Legion has support for fields of arbitrary types, but we haven't piped through the structure types into Legion yet. But that's not a hard thing to do, and so if that's important to people, that would be sort of again something that would be interested in hearing feedback from users about what kind of types and stuff they would like to see.
Can you do complex numbers?
We do not do complex numbers yet. That is on the to-do list of very high priority things. We have some folks who are very interested in doing some quantum simulation stuff with Leagate, and so complex numbers are rapidly moving up the to-do list, but they're not there right now at the moment.
All right. Well, thank you very much. I think we're over time, so we should wrap up. But thank you, Mike. Thank you to all of our speakers. Thank you to Andreas, who's been making this all happen behind the scenes. Thank you to Kristen and Jill, who've also been a big help organizing and putting on this session. Thank you, all of you attendees and people posting good questions and comments in our chat.
Thank you, Lori, for organizing and walking us through the session so seamlessly.
Good to see you all. Glad to see that people are so interested in high-performance Python.
Hope you enjoyed it. And at this point, since we're a little bit over, we should wrap up. If you have further questions, as Lori said, we'll see you in the Slack channel.